Welcome back. So this is lecture 19 in this course on Bayesian modeling. The topic of today's lecture is prior predictions and posterior predictions. So far in the previous lecture, what we have covered is that how do you calculate the posterior distribution. This is basically part of parameter estimation. So given any experiment and given any data, you make some assumptions that what could be the underlying generative process behind the data, right? And what kind of assumption we make? We assume some form of probability assigner function. So probability density function or probability mass function, right? So that's the kind of generative process we assume, right? Now that probability mass function or probability density function would have certain parameters which determine that exactly what kind of data it is going to generate, right? So because it has parameters, you need to estimate those parameters given the data, right? So once you collect experimental data, you need to estimate that what are the likely values of that parameter that might have generated the data, right? And in order to do that in the Bayesian framework, we calculate posterior distribution of the parameter. So we do not calculate a point value of the parameter, we calculate which values of parameter are more likely, which values are less likely, given our prior assumptions and the data, right? And that's our posterior distribution, right? So we calculate a posterior distribution given likelihood function, which is basically which comes from our likelihood assumption, our assumption about how data was generated, and our prior assumption about the parameters, right? So you multiply them, which gives us a normalized posterior distribution. You can normalize it by dividing it by the marginal likelihood. Okay, so that's how we calculate the posterior distribution. So we saw for very simple cases that how you can calculate posterior distribution computationally. Okay, now there are a couple more things which are very useful in Bayesian modeling, which I'm going to discuss in this lecture. Okay, and these things are that you can generate predictions from your model, and these are not point predictions. You can generate a whole distribution, right? So what kind of data you might end up seeing in some future experiment, right? So that's prediction, right? But you can actually generate two kind of predictions in Bayesian modeling. Okay, the first kind of prediction is called the prior prediction. Okay, this is the prediction you can make before even seeing the data, right? So what else happens before seeing the data? What you have before seeing the data, right? So before even seeing the data, when you are planning the experiment, so this is in the planning phase of the experiment, you make two crucial assumptions, right? We discussed this earlier as well. You make the likelihood assumption and you make prior assumptions about the parameter of interest. Okay, so you make these two assumptions even before seeing any data. So let's say hypothetically you are doing an experiment where the participant has to recognize whether the sentence they see on the screen, it's a acceptable grammatical sentence or not. So let's say they see on a screen the key to the cabinets are rusty. Okay, key to the cabinets are rusty. So the participants have to respond with the key whether this sentence is acceptable or not. Now this sentence is not grammatical because this verb is plural and the subject which is referring to is singular, right? So in most cases participant will answer with that this sentence is not acceptable, but sometimes they might even say that this sentence is acceptable. They might ignore this or they may get some illusion that this is acceptable, right? So this is the task. So the task of the participants have to judge whether this sentence is grammatically acceptable, whether it's an acceptable sentence of English or not. So you can call it acceptability judgment task, right? So let's call it acceptability judgment task. And what we are going to record in this task is the judgment times. So how much time do they take to judge the sentence? So they will respond with yes and no, but how much time do they take to respond, right? we are interested in judgment times. Okay. So, suppose you are planning this experiment, you haven't collected any data, right? Even in this phase, when you are just planning the experiment, right, you start with assumptions, and in fact, this is the phase where you should have your assumptions ready even before seeing any data. Okay. So, you need to make the likelihood assumption and the prior assumption. So, what is the likelihood assumption? Basically, your assumption about generative process behind the data. So, what kind of data you are going to observe in this experiment? Judgment times, right? So, these could be in milliseconds, let us say 1000 millisecond, 1500 millisecond, 600 milliseconds, like that, right? So, how much time do they take to press a key after they see a sentence, right? So, that is judgment time. So, that is what you are interested in recording. What could be the underlying generative process behind these judgment times? Okay. So, let us see. So, one distribution that you have seen that could be very suitable here is the log normal distribution. So, let us say you assume that judgment time in the ith trial comes from a log normal distribution with parameter mu and sigma. So, this is your likelihood assumption, that judgment times in this experiment are generated by a log normal process. Okay. A log normal distribution ensures that all these judgment times are positive and you have a longer tail on the right hand side, which is how the typically judgment times or reaction times look like. Yeah. So, this is your likelihood assumption. Now, you have two parameters here, mu and sigma, and the Bayesian framework, both these parameters will be treated as random variables, right. So, they both will have some underlying true distribution. Okay. So, they have both these parameters have some underlying true distribution, true probability distribution, but we do not know what is that true distribution, right. But in order to make inference, what we can do, we can have some prior beliefs or prior information or prior assumptions about the distribution of these parameters mu and sigma. Okay. And in most cases, for example, in experimental setting, this might depend on your experience. So, let us say if you have done some judgment studies in the past, if you have done these sentence acceptability judgment studies in the past, you would have some idea that what would be the likely values of mu. Okay. Because you have fitted similar model in the past, you might have used log normal distribution for data analysis. So, you would have some idea that what would be likely values of mu. Okay. So, for example, based on my experience, I have this idea that mu would be somewhere around 6. So, let us say I define this prior on mu. Okay. It is a normal prior with mean 6 and standard deviation 1. So, this is my prior on mu, that this parameter mu can have values between, let us say 4 and 8. Okay. So, which is a quite weakly informative prior. Okay. Now, there is another parameter sigma. Okay. What do we do with sigma? Well, just for simplicity, of course, you will also define a prior on sigma, but just to simplify our case for this example, let us think, let us say sigma is fixed at 0.25 or something. Okay. But you can also define a prior on sigma. For example, it could be a truncated normal prior which can only take positive values, right. So, these are our prior assumptions. So, I have defined likelihood assumption and prior assumptions before even seeing any data, right. Now, you can generate prior predictions from this model. What is model? Model is just the set of the assumptions you are making here. So, in this case, your model is your likelihood assumption and your prior assumptions. That is your model, right. Now, you can generate prior predictions from this model. What does that mean? That given your assumptions, given your prior assumptions about the parameters, okay, given your prior assumptions, what data model would generate. Okay. So, you have a prior belief that this parameter mu is somewhere around 6 and sigma is equals to 0.25. Given this prior belief, prior assumption, okay, what kind of data the model would generate on a judgment task, right. That is what we want to figure out, and that is what we call prior predictions of the model. Okay. So basically this is the predictions of the model under prior assumptions before seeing any data at all, right? So this is before seeing any data. Okay, so this is our prior predictions before seeing the data. Okay. So in fact, you are making these predictions for the current experiment, the experiment that you are planning right now, for which you haven't seen the data. You are still in planning phase of the experiment, right? You are making predictions about that experiment, that what is going to happen in this experiment given my prior belief and my prior assumptions, right? So you can generate prior predictions now. This thing is called model. This is a set of your likelihood assumptions and prior assumptions, right? Now you can generate prior predictions of the model. There are more technical name for this. You will see prior predictive density and prior predictive data, right? Which actually you would see technically more used in this context. But basically the point is same, that we are trying to generate prior predictions of the model. Okay. How do I generate prior predictions? Well, it's not very different from any case of how you generate predictions from a model. If you have done this earlier for frequentist modeling as well, the idea is same. That idea is to simulate new data from the model, right? How do we simulate data from a model? How do we generate new data from a model? Like this. So you know that reaction time in ith trial will come from log normal mu sigma, right? So what if I simulate 1000 trials? That will depend on what you are planning, how many trials are planning in the experiment. So you generate as many trials as many you are planning in the experiment. Okay. So or let's say 100 trials just for simplicity. So let's say you're planning an experiment with 100 trials. Okay. So can you generate reaction times for 100 trials under the assumption that all the reaction time in the ith trial comes from a log normal distribution? You can, right? You know how to generate from log normal distribution using RL norm. For example, if it would have been a normal distribution, you would use R norm. Basically, we need to generate random values. We need to randomly draw values from a log normal distribution with parameter mu and sigma. And how many values we need to generate? 100, because that's the sample size, number of trials. But the problem here is this, that in order to generate these values, right, you need to know point values of mu and sigma, right? In order to generate randomly 100 values from a log normal distribution, you need to know mu and sigma. You need to know on what values of mu and sigma you are trying to draw from this distribution, because the distribution will change drastically as mu and sigma will change, right? So it's important to know mu and sigma, otherwise you cannot even use this function in R, right? So where would values of mu and sigma come from? They will come from your prior distributions that you have assumed here, right? What you have assumed? Mu, you have assumed normal 6, 1 prior. So what if I draw lot of samples of mu, okay, from its prior distribution, which is a normal distribution. Let's say I draw 100 samples of mu from normal distribution with mean 6, standard deviation 1, right? And sigma is actually remains fixed, so we don't need to worry about it. So sigma is always 0.25. Now you have 100, or let's say 500, just to make a distinction. Let's say 500 samples of mu from its prior distribution. Now corresponding to each sample of mu, you can generate a prior predictive sample, right? So let's say I iterate for I in 1 to 500. So as many samples from the prior you are collecting. So this step is called collecting prior samples, or let's say drawing, more precisely, drawing samples from prior distribution of mu. So basically you are drawing 500 samples from the prior distribution of mu. Now for each sample of mu, okay, from its prior distribution, you would generate prior predictive sample. So each sample that you would generate would be called a prior predictive sample. And how you generate it? Using RL norm, because that's the likelihood function, right? So that's the data generative function you have. Okay, so you are assuming that data in each trial comes from a log normal distribution. So that's your data generative function. So use RL norm. How many observations you want in each sample? 100. Now mu, value of mu will be mu I. So basically ith sample of mu from its prior. Okay, and sigma is fixed as 0.25. Okay, so that's how you can generate prior predictions. Now what this will end up giving you is this. This will give you actually 500 prior predictive samples. So let's say this is the first sample. Let's call it XM1. Let's call it XM2. Let's call it XM3. Let's call it XM500. You will get 500 prior predictive sample, where each sample will contain 100 observations. Basically your sample size, whatever sample size you wanted, right? Right. So this is how the prior predictive data looks like. This is called prior predictive data. So you have 500 samples of posterior of prior predictions from the model, okay, where each sample contains 100 observations, right? What does each prior predictive sample mean? So you can call it prior predictive sample, right? What does each sample mean? Well, each sample indicates an experimental data, right? So if let's say your prior assumptions and your likelihood assumption, if they are all right and correct, if they are correct, right, then and then you do experiments, like repeatedly if you do experiments, then each time this is the kind of data you might see. So your prior predictive sample represents the actual experimental data that you might see, right, if your prior assumptions are correct about the parameter. What do we mean by correct? If they closely match the true distribution of mu, right? If that is the case, then your data would look like your prior predictive samples. If you repeat the experiment multiple times, you will see the same distribution as these multiple prior predictive samples have, right? So each prior predictive sample is simulating data for a single experiment, okay? But why do we need so many prior predictive samples? Because of randomness. So whatever happens in a single experiment, you are not likely to replicate it exactly in the next experiment, right? So across experiments there would be randomness, right? Because if the true distribution of mu is, let's say, normal 6, 0.05, even then the value of mu for some experiments could be 6.1, for some experiments 6.02, and like that, right? And depending on value of mu, the data that will be generated in a particular experiment would look different. So data in this experiment look different from this one, right? So that's the idea, okay? So let me describe the whole process of generating prior predictions step by step, okay? So maybe it was not very clear algorithmically. So let me describe how to generate prior predictions from a model, okay, step by step, okay? So suppose this is your likelihood assumption that observation in the ith observation comes from this data generative function f of x theta. In our example, it was a log normal distribution, right? So let's say this is your likelihood assumption, or you can call it data generative assumption, okay? Then you have your prior assumption. So let's say theta comes from p of theta. So that's your prior assumption, okay? Now we have likelihood assumption and the prior assumption. Now you can generate prior predictions from the model. How? what you can do is this, that you determine how many samples you need from the prior. So, how many prior predictive samples do you need? So, let us say you decide that number would be, so you can call it number of simulations. So, let us say you want 500 simulations, okay, and then you also need to determine sample size, okay. So, or you can call it number of observations. So, number of observations that you want in each sample. So, let us say number of observations you want in each sample is 100, because that is the experiment you are planning. You are planning to collect 100 observations in your experiment. So, it should match the number of observations you are planning in your experiment, right. So, this is the number of prior predictive samples you are going to have, and this is the number of observations in each sample, okay. Now, you can iterate through these 500 simulations. So, for I in 1 to n sim. So, I am going to generate a prior predictive sample corresponding to each sample from the prior, right. How? So, I am iterating through all these 500 simulations. How? For each simulation, I just need to draw theta, okay. So, draw theta from its prior distribution P of theta. How do I do that? Suppose prior distribution is normal, then I would generate, let us say, theta from R norm, right. So, I can use R norm function. So, depending on what your prior distribution is, right, and whatever the prior distribution was, let us say 6 1. So, this will give me theta from this prior distribution normal 6 1, right. So, basically draw a single value of theta, okay. So, draw a single value of theta from its prior distribution. So, draw a single value of theta from P of theta, which is its prior distribution. So, that is the first thing you will do inside this loop, okay. So, we are going to do these things inside this loop. What is the second thing you will do? Now, you have a value of theta. Now, corresponding to that value of theta, you can generate a prior predictive sample. So, I will generate x sim I. So, this is the ith prior predictive sample, and how do I generate it? I just need to draw this from f of x theta, right. So, for example, if the data generative function you have assumed is a normal, if your likelihood assumption is normal, then you can just use R norm and theta is given. So, point value, let us say theta star, let us say point value is theta star. So, you can use theta equals to theta star and generate from R norm, which is your likelihood assumption, right. So, what you are going to do here is basically draw a sample of data points, okay. Let us call it y 1 2, but how many data points? As many observations you want to collect, y 1 to n obs, right. So, n obs data points from f of x theta equals to theta star, which is the point value that you have just drawn from your prior distribution, okay. So, you have drawn a value from prior distribution and then you use it to generate n number of observations, okay. Fine. Third thing that you will do, now basically you can store all these samples inside a single data frame. So, maybe, so there are different ways in which you can do this. So, let us say you use some function like R bind, binding by rows, where you basically combine this data that you have just generated, this particular sample, into overall prior predictive data that you are trying to generate, right. So, this is what you do inside the loop. Okay, so what you are doing is this, that for each iteration you are drawing a sample of theta. You are drawing a sample of theta from its prior distribution. Then conditional on that particular sample of theta, you are generating new data from your likelihood function. And how you are generating new data? You are generating n obs. So let's say in this case 100. So 100 observations from this function, right? So you generate as many observations as you want, for example, depending on your experiment. Okay? And then you are storing them together, right? So that you have all prior predictive data in a single data object, right? This is the process of generating prior predictions. Now, once you have run this loop, this will take some time, by the way. After you are done with this loop, what you can do now, you can actually summarize predictions. Okay, you can calculate summary statistics of prior predictions. Okay, because it would be very difficult to visualize this whole prior predictive data in a single graph or anything, but you can visualize summary statistics. What does that mean? Because you have collected how many prior predictive samples you have? You have this many prior predictive samples. So let us call them ypred1, ypred2, ypred3, ypred and sim. So you have these many prior predictive samples, right? So what you can do is this, that for each prior predictive sample you can calculate its mean. So it's a mean of ypred1, right? Similarly, mean of ypred2, ypred3 and so on. Now you will have n sim number of means, right? So you will have mean of predicted data from 1 to n sim, right? Now you can draw a histogram of these means, right? So which might look like this. Okay. So this is mean or average of prior predictive samples. Okay. And what does this mean? What this graph shows you is this, that under these certain prior assumptions, under the assumption that theta comes from P of theta, under this prior assumption, okay, what would be the distribution of average response across, let's say, 500 experiments. Okay, so under this prior assumption, if you repeat the experiment 500 times, what would be the distribution of average response or whatever average observation, average value of the observation you're recording across, let's say, 500 experiments, right? That gives you a very good idea of how your data would look like under these prior assumptions. So if these prior assumptions were true, how the data would look like. Now the point is, what is the use of this? Why we are interested in generating prior predictions? And you will in fact see that prior predictions looks very weird. If you, especially if you choose weakly informative prior predictions would look all over the place, right? But why they are useful? Exactly for that reason, that to ensure that your prior predictions do not look all over the place, they look reasonable, right? And why does that matter? So let's say you are doing this even for the experiment that we were planning here, right? For this particular experiment, for judgment times experiment. So let's say hypothetically you assumed that the prior on mu is tan 1. Okay, so let's say you do not have a very good idea and you just took a guess and you decided this prior seems okay. Okay, so prior normal tan 1. Okay, if you decide this is your prior, what will happen in this case is that all the prior predictions that you will see, all the prior predictive samples you would see, the judgment times would be in the range of 2000, 4000, 5000, like 10,000 milliseconds, up to 10,000 milliseconds, right? Is that possible? No. So judgment times can't be that long. So these are simple key press times that making some decision and pressing a key. So these are like reaction times. They would be around 300, 500, or maybe up to 100, up to 1000. but they can't be 10,000 milliseconds because that means 10 seconds, right? So that is unreasonable, right? And where this weird outlier kind of data coming from? Because of your prior assumption. You have already assumed that the value of mu is very large, somewhere around 10. If that is your assumption, then the prior predictive data is going to look like this, that you would expect that your experiment would have observations like 10,000 milliseconds, right? And that is bad, because what is bad? Actually, your prior assumptions are unreasonable here, right? Because if you assume that this is the prior on mu, that this is a true distribution of mu, right, you are making very strong assumption that in this experiment you are going to see only very large judgment times, right? And that's not really true, because judgment times are typically in the range of 300 to let's say 1000 milliseconds, right? So it's a very important check for your priors, and that's the use of prior predictions, right? So before even going into parameter estimation and estimating the posterior distribution, so before going into process of inference, what you should do first is to check whether your priors make sense or not. In fact, even before collecting any data, you can check this, okay? Because even before collecting any data, you would have some idea about what kind of data you might see in your experiment. So let's say you're expecting that in this experiment I might see data which is, let's say, which has a median around 400 milliseconds and can go up to, let's say, 1500 milliseconds, and minimum value can be up to, let's say, 50 milliseconds. So let's say this is your idea, that this is the kind of data you might see in this experiment. It could be a bit off here and there, but that's the basic idea that you have about your experiment. Now you can check your prior predictions, whether your prior predictions look similar to what you are expecting in this experiment, okay? If your prior predictions look very off, way off, let's say your prior predictions look like this, that median value is 10,000 milliseconds, minimum value is, let's say, 2000 milliseconds, and maximum can go up to 50,000 milliseconds. If that is the case, then your prior assumptions are unreasonable. You can say, let's say, they do not make any sense, right? So you need to revise your prior assumptions, make some reasonable prior assumptions. So this usually happens in the situation where you do not have any prior experience, when you do not have any idea about what could be a suitable prior for this parameter. There are no previous studies on the same phenomena, and you are choosing a completely new likelihood function, and you do not know how this likelihood function behaves, right? In that situation, this could happen, right? So it is very important to do a prior predictive check. This is called a prior predictive check, that you generate prior predictions from the model and try to visualize whether they seem similar to your the kind of data you're going to observe in this experiment. Do these prior predictive data look reasonable, okay? If you do not know what kind of observation you will see in the experiment, you can also compare it with actual observed data after collecting the data, okay? So that's fine, because we are not making any inference about the underlying process by using this data. Only thing we are trying to check here, whether your prior assumptions make any sense or not, right? So this is an important check, especially in the situation where you do not have any prior experience or prior information about your parameters of interest. If this is, let's say, completely new phenomena and you have no idea what kind of prior you can choose, right? This situation is rare, but this still arises, right? So it's actually it's a very good practice to always generate prior predictions and see how it looks compared to observed data, right? And we will see another very important application of this in model comparison, but that's a point for some later lecture. But at this point, you should know how to generate prior predictions of a model, right? In the next lecture, we'll practice how to generate prior predictions in R and also posterior predictions. Now, posterior predictions is just slightly different from the prior predictions in the sense that once you have estimated your posterior after seeing the data, so after seeing the data, you can estimate your posterior distribution, right? So let's say this is your posterior distribution. Okay. Now you use this posterior distribution to generate predictions for future data. Okay. So, rather than drawing samples, remember in prior prediction generation, you are drawing samples from the prior. Okay. So, rather than drawing samples from the prior, you can draw samples from the posterior. Okay. Now, posterior basically contains information from existing data and your prior assumptions and everything, right. So, now you draw samples from the posterior distribution and generate future predictions. So, what is the kind of data that you might see in future experiments, right. That is called posterior predictions of the model, right. So, we will see how to generate prior predictions and posterior predictions in R, okay, in the next lecture. All right, thank you.